So we're on magnetic fields. There's going to be about 3 or 4 chapters which are to do with magnetism or electromagnetism. The things we're going to talk about today are we're going to talk about this idea about the magnetic field. Its symbol is B because we ran out of letters, so its symbol's B. And we're going to talk about what's quite an interesting area, which is the effect of a magnetic field on a moving charge. And in fact, if you go to places like CERN, you find that all of that system uses magnetic fields to steer those charged particles. We're going to talk about an application of this, which is the so-called fine beam tube, which I'll show you in a few minutes, which is over here. You're going to do that as a lab in, I think, 2 labs' time. Then we're going to talk about a brief comparison between the B field and the E field. We're going to revise a bit of math. We did this with, can you remember what part of Physics 1 we used the cross product in? What was it?
It was the force of an angle.
So what part was that? So there was a bit where you did forces with displacements, and they had to be in line with each other. And that gave you the dot product, and that was work. And then the next bit was torque, where you had a force and a distance that were perpendicular to each other, and that gave us torque. So we've got to review that. If you've not done that in a while, then review that, please. We'll go through it again here. And then we're going to use some cross products, and we're going to talk about basically 3 equations which use the cross product. And as a visual thinker, I kind of feel in a way it's a bit cheating. It kind of like takes the visualization out, but it gives you the answers. It makes a complicated system relatively straightforward because of that. Let's talk about bar magnets. If I put a compass, as you guys did in lab, if you put a compass near a bar magnet, I can trace out a magnetic field. The compass basically aligns itself, the needle points, and you can do head to toe and trace it around. And they seem to come out of one pole and enter the other pole. And we need to have a direction for this because fields have directions. And so we talk about the magnetic field lines coming out of the North Pole and going into the South Pole. And the way we remember that is we look at our finger because we're going to point in the direction of the magnetic field. And, you know, the joke is you look at your knuckle, which begins with N. It doesn't, but... And look at the tips of your fingers, which ends with S. So the arrow, if I can... So the arrow kind of goes along in line with your finger. So it points from north to south. So you're pointing in the southerly direction. So you go like that. Cool. We see regions, as with electrostatic fields, where there's a lot of lines in a small area, and we see regions where there's few lines in a small area. And, you know, that symbolizes the magnetic field's intensity. So we have a lot of analogies with the electrostatic field feeling, the gut feeling we had for electrostatic fields. There are some contrasts, though, and I want to briefly talk about those. With electrostatic fields, the electrostatic fields actually started on a positive charge and went towards a negative charge. So the electrostatic fields had a beginning, the lines, they're imaginary lines, of course, but they had a beginning point and an ending point. And I could, if you like, take this charge and put it in an envelope and send it all the way across to Australia. And although both charges would exist, to a great extent, this guy would look like an isolated charge. Whereas in the magnetic field, the lines seem to come from a North Pole and go to a South Pole. We decide that. We say we're going to have them in the external space go from north to south. But you know what? If I could go inside the material, I would see these lines continue. So they're not starting or ending anywhere really. They're just entering the bar magnet and leaving the bar magnet. And so there's a fundamental difference there about you don't have a start and ending point for a magnetic field line. It's a closed loop. And that's going to have ramifications all the way through. But beyond that, you know, we can still use this idea of flux, and we can still use this idea of flux density, and we can go on from that. It's just there's these slight differences between the two systems. We say that the SI unit for magnetic field B is the Tesla. A Tesla is a huge size of magnetic field. The Gauss is more traditional. And the Gauss is, in a way, we like things to go from 1 to 100. We feel comfortable with that. Maybe 1 to 1,000, but when we start getting into the tens of thousands or hundreds of thousands, the numbers all become similar, yeah? So they're big. So the Gauss is actually a really quite approachable unit. But it turns out that from the SI unit, when you work the SI math, the number you come out with is the Tesla. And so we talk in terms of Tesla. But you will see Gauss all over the place. So just realize there's a conversion factor. You don't have to know it, but realize there's a conversion factor between the two. Magnetic poles are designated as north and south. And the single magnetic pole has never been isolated. You know, that's actually taken directly from the book, and I always have a little bit of pause about that because I'm not sure a single magnetic pole could be isolated. Because they are really two aspects of the same thing. If I was to cut this bar magnet in two, then what I would get are two bar magnets, and there'd be a north pole and a south pole on each bit. And so the argument goes, well, supposing I cut it in four. Well, I end up with a north pole and a south pole and a north pole and a south pole and so on. So you go down, you get to the stage where you have a plane of atoms. Surely now that plane of atoms must be either north or south. And it turns out it's not. If you look at the atoms from one direction, they will be north. And if you look at the atoms from the other direction, they will be south. Now, we don't worry about that. If I hold up a piece of paper and say, I wonder if I could get the front face by itself or the back face by itself, you'd say, this is crazy. The two faces are the same thing. You can't. I mean, if you split it, you can have two pieces of paper. So it doesn't worry you about pieces of paper. And yet people get very worried about this. And I think it's partly just the visualization. Magnetic fields are caused, well, we model a magnetic field as being caused by a spin of an electron. And in some atomic species, in the outer shells, there's unbalanced electron spin. So if you imagine, I'm going to draw the atom as spinning rather than the atom as spinning. But imagine I have a series of atoms. I've got a magnet made up of 4 atoms that form a plane. And it turns out that they have a spin. I'm going to show the spin like that. They're all spinning in one direction. They're all spinning clockwise as I look at them going like that. And it turns out if I look from one direction, I will see a north pole. And as I look from the other direction, I will see a south pole. So the north and south pole are they're not so much things as they are the aspects of a thing. And we can still think of it as the end of a piece of metal. But we're not going to find a monopole. Magnetic field can be represented by magnetic field lines, and we're showing that there. Magnetic field lines form continuous loop, and that's, again, in contrast to what we found with electrostatics. Magnetic field lines extend from the North Pole to the South Pole in the region outside the magnet. We've just got to remember, because next time we're going to do a lab where we look at the magnetic field inside a magnet, we're going to use a slinky with a current flowing through it to cause a magnetic field. It behaves just like a bar magnet. But now we can puncture that magnet, and we'll look at the magnetic field inside the slinky. So similarities and differences, and it's always good when you get similarities and differences, just compare and contrast. Our first observation, if I have a charged particle, say it's a positive, in a magnetic field, then it will, if it's moving, feel a force. If it's not moving, it will not feel a force. If it's moving faster, it will feel a bigger force. And then the kicker is, the force is not even in the direction of the magnetic field. The force is, or the velocity, it's at 90 degrees to both of them. And so what that tends to lead to is when you get a motion and the force has a component in line with the motion, that force causes an acceleration in line with the motion. And so what happens to the speed of the particle under those circumstances? If I have a motion and an acceleration in line with the motion, what happens to my speed? Does it stay the same or does it change? It changes, doesn't it? Now, if I have a motion and I have a force to the side, like we had in Physics 1 under some circumstances, what happens when I have a forwards motion and I have a force to the side? What's that going to do to my motion? Am I going to speed up or slow down if the force is 90 degrees to my motion? My speed will stay the same. But what will happen? There must be an acceleration if there's a force. So what's going to satisfy the acceleration? Change in direction. And what kind of direction do I typically get? What kind of pattern do I form? A circle. So we're back with circular motion. So again, if it's been a while since you did circular motion, you might want to look back at that. So I find I have this force, we call it the magnetic force, and the magnetic force, it depends upon the charge, it depends upon the velocity of the charged particle, it depends upon the magnetic field vector. And we don't justify it, it just comes out of a hat. A lot of this stuff just comes out of a hat. What we say is that it's Q V cross B. The order with cross products matters. Okay. If we have B cross V, it goes in the wrong direction, and that's the worst option when you think about it. If you want to go to Orlando and you drive north, when you think you've got there, you're twice as far away from Orlando than you actually started from. You've made your situation much worse. So if you get the wrong sign in these things, although mathematically it's a mistake, it's actually from a physical point of view the worst outcome you could get. So consequently, magnetic force is perpendicular to the plane containing the velocity vector and the magnetic field vector. So here I've drawn it. Here's the B vector, and here's the V vector, and we have our force vector at 90 degrees to those two. The B vector and the V vector I've drawn at 90 degrees to each other because that's the simple case. But it turns out they don't have to be. I can have them quite close to each other with just a slight variation. Here's my B and there's my V. And my force might not be as big, but it will still be at 90 degrees to that combination. Well, it could be up and it could be down. So I need to figure out which direction it is for my force. And for that, we use, this cross product will tell us, but we can also do it by hand. So I want you to hold your hand out like this. This is the right hand rule. There's about 5 right hand rules. So this is the right hand rule. And this works really well when things are at 90 degrees to each other. So the first thing I want you to do is I want you to take your thumb, and that is the motion. Okay. And then I want you to look at your fingers, and you have knuckles and tips. So that's your magnetic field. And then the palm of the hand, that's the force. Okay. So if my motion of my charged particle, positive charged particle, is upwards, and my magnetic field is pointing away from you, then the force will be to your left. Okay? So you just get used to doing this. And when we're doing the test, I'll see people doing this all the time, trying to figure it out. Sometimes you'll see a variation of it like that, but basically that's the way I was taught, was like that. That works great for 90 degrees. And it works great for motion and magnetic fields and the like, but we have cross products all over the place. So there's another way we can do this, which is we look at the mathematical expression. Forget the Q. I'm not bothered about the Q. I'm trying to get the direction. The direction depends upon your velocity and your magnetic field. And what you learn with this is that when you look at any cross product, if you take your fingers and you point towards the first vector, and then you do what it takes to rotate towards the second vector, your thumb will point in terms of the cross product answer. So let's say my first vector is towards the flag. So point your fingers towards the flag. And then let's say the second vector is towards the floor. So twist your hand until you can comfortably bend your fingers towards the floor. You don't want to be kind of going backwards, double jointed. Just twist it and bend down. And which direction is your thumb pointing? Points towards your left, okay? So for small variations, only a few degrees, you can still get the correct value. Let's do one more. Let's do towards the whiteboard, please. First vectors towards the whiteboard. Second vectors towards the ceiling. Curl your fingers towards it. Which way does your thumb point? Towards the flag. So it's kind of nice. So we say, consequently, magnetic force is perpendicular to the plane containing the velocity vector and the magnetic field vector. Consequently, the magnetic field changes the particle's direction, but not its speed, because there's no component in line with the speed. The sign of the charge affects the direction. Do it for positive. Then, if the question asks you for negative, just change your answer. Do the opposite. Okay? But don't try and remember different rules for different charges. Just do it for a positive charge, and then if the sign's negative, do the opposite. Then we often want to know the direction of the magnetic field will act on a moving charged particle. We can use the right-hand rule. And there's two versions of the right-hand rule, and I just showed you them both. Okay. Let's review a little bit. So we have our, these are the same notes I showed you in Physics 1. These are the cross-product notes. So basically, I have a vector A, and I have a vector B, and there's a certain angle between them. And the cross product will be at 90 degrees to the plane containing the A and the B. We say a cross product or vector product, same thing. We can say, well, the magnitude is going to be the magnitude of A times the magnitude of B times the sine of the angle between. And remember to compare and contrast. A dotted with B would have a magnitude which is the magnitude of A times the magnitude of B times the cosine of the angle between. So dot products work great for things that are in parallel, but they're not good for things that are perpendicular. Whereas cross products work great for things that are perpendicular, but not so good for things that are parallel. So basically we can say that this is commutative, so A crossed with B is not equal to B crossed with A. And that's because of a directionality issue. It's the wrong direction. We can say the vector product is distributive in multiplication. So A crossed with B plus C is A crossed with B and A crossed with C. For a perpendicular, if A is perpendicular to B, we have A crossed with B is equal to the magnitude of A times the magnitude of B times the sine of 90, which is 1. So we can just forget it. And for parallel, we say it's A crossed with B is A times B times the sine of 0, which is 0. The derivative of A crossed with B with respect to T is this. So this you don't really, I'm going to use it in a derivation, and you don't need to know this for the test. Because we just use it to explain something. But if I have dA crossed with B by dt, it's A crossed with dB by dt plus dA by dt crossed with B. So, vector product and unit vectors. A vector product is two parallel. So when I was a student, I remember getting to this bit and just blew it off. It was like, who cares, you know? And what I've realized as I've got older is that the more familiar you are with the kind of basic stuff, the better it is for the complicated stuff. So basically, I is in the plus x direction. So I crossed with I, well, you didn't get any angle, it's 0. And j crossed with j and k crossed with k are all going to be 0. But now, I crossed with j has me pointing, I crossed with j, so I'm going to do it your way. I keep trying to do it. So I crossed with j gives me a vector which points out towards you, which is k. Yeah? And minus j crossed with minus k, j crossed with I. Again, I'm doing it that way. J crossed with I gives me k. Is that right? K. Minus j crossed with I. I'm sorry, I can't read. Minus j crossed with I gives me coming out towards you. J crossed with K, so J crossed with K gives me pointing in the positive X direction, which is I, and so on. Just don't let that stuff put you off. Just embrace it and visualize it, and just once you're satisfied, it's okay, it's okay. And then how do we do them? And remember that in Physics 1, I just like to get on and do it. So let's just do one of these. I'll remind you of it, and then you can do some practice. So we're going to say, okay, what's the vector of V cross B given that B is, and we're going to have 3I plus 4J minus 2K Tesla. And then I will have 2I minus 3J plus 3K meters per second. So I don't know which direction these are in. I'm just imagining them in these directions. And what I do is I say, okay, I'm going to go I, J, K. And then I've got to make sure I have the first one. And my first one is going to be V cross B. So I want to find my V. So that's plus 2, and this is minus 3, and this is plus 3. And then for my next one, it's going to be my B. And my B is going to be plus 3, and plus 4, and minus 2. And so what I do is remember what we do? We put our thumb over the I column when we're doing the I column. And we put our thumb over the J column when we're doing the J column. We put our thumb over the K column when we're doing the K column. We cross-multiply what's visible. And we've got one more wrinkle to remember. So let's start off. And I'm going to go 2 times 4 minus 3 times 3. And that's going to be my term for my I. And then I'm going to add on, oh no, let's stop, I'm there, I got it. Then I'm going to subtract.
Your eyes are
Hold on. My eye's wrong? Man, that is shame on me. Shame on me. Okay. So let's do that again. Minus 3 times minus 2 minus 3 times 4. Thank you. I minus. So there's the wrinkle bit, and that is that second term has to have a negative sign. The first term has a positive sign. The second term has to have a negative sign. The third term will have a positive sign. So I go 2 times minus 2 minus 3 times 3 J, and then plus, I'm going to do my last term, which is 2 times 4 minus 3 times minus 3. Okay. So we're going to go 6 minus 12 I minus 4 minus 9 J plus 8 minus 9 K. Did I do that right? 6 minus 12 and minus 4 minus 9 and 8 plus 9 because it's a minus 9. So that's going to be minus 6I, and that's going to be minus and minus makes minus 13, and that makes plus 13 J, and then that's going to be 17 plus 17K. And hopefully the answer's there. Minus 6, 13, and 17. Agreed? Now, the only shame on this, I forgot something. I actually did improve on this. I forgot something. I put this down as the answer. I'm going to get dinged a little bit. So why will I get dinged on that? Yeah, I need to have a B cross V or a V cross B, I'm sorry. So it's going to be Tesla meters per second. If you put down meters per second times Tesla, it's just as good. But you've got to have your units. You can't just not have your units because it's 9JK. Okay. Can you ever go at that one for me, please? And what I'm going to do is I'm going to put the timer on. And I'm going to pause this so we have a bit more time on that. So, just looking at this, I didn't record that. So briefly, I put down my equation. I visualized. I wrote my grid down. I did my cross product. And then I remembered to multiply by the Q at the end. And I got my answer. Put my units down, yes.
Why are they unit vectors? Don't you have to divide by the magnitude or something like that?
No. I can represent a vector by so many I vectors, so many J vectors, and so many K vectors. So it's literally, it's this number, it's 5 I's. So the actual component is 5 I's. And so I'm not finding a magnitude here. I'm finding a vector.
Right.
If I want to find the magnitude, I will use Pythagoras on this and find the magnitude. And if I want to find the unit vector, so actually let's review that because it's kind of useful.
Right, I get the unit vector is the vector divided by the magnitude, right?
Yes, yeah.
So how is that a unit vector? Is that just, we're assuming it is?
How is what a unit vector?
With our final answer with the force.
Oh, it's not a unit vector.
Then why do you have the hats over the letters?
Because the total vector is made up of 5 unit vectors end to end.
Okay, I see.
Yeah. That unit vector means one in the x direction. Yeah, cool. I should have said they are unit vectors. Yeah, okay. Let's make it a little bit more interesting. Let's say I have a 3 coulomb positive charge. And let's say that it's moving at 6 meters per second in the positive x direction. And it's in a magnetic field, which is 2I plus 3J plus 4K. Tesla. And I want to find the vector force. What's the strategy? What am I going to do to find this? First thing I'm going to do is write down my equation. What's the governing principal equation? FB is equal to Q V cross B. Yeah? And we can expand that, can't we? So what would that be if I expanded it? It would be Q. And then if I just wanted the magnitude, what would I do? I would put down V, B, sine the angle between. Yep. That's the magnitude. And that's the vector, yeah? But if I asked you for the magnitude, what route would you take? Would you try and find this angle? That's a bear. In 3 dimensions, that's a bear. So the better way is you say, oh, this is going to be 6I plus 0J plus 0K meters per second. Convert that second item into an IJK vector. Then do your cross product. And then if you need to have the magnitude, just do Pythagoras on your answer. Okay? So remember with dot product, well, specifically with dot products and cross products, I can give you a magnitude, and an angle, and say, what's the answer? And you can only give me a magnitude as the answer. I can give you a vector IJK and a vector IJK and ask you for the answer. In one case, you'll get a magnitude because it's a scalar. In the other case, you'll get a vector because it's a vector. But I could ask you for the magnitude of the cross product, in which case, don't get fooled into doing the QV cross B sine the angle. Still do your cross product, but then find your magnitude of the cross product. Okay? Okay, cool. Let's look at this. This is a great piece of apparatus. Can you all see it okay, or do you want to come round? Let me come round. This is the so-called fine beam tube. And this is, did an amazing experiment. You can sit where you like if you want. It's all right. I don't mind. But there's a lot of stuff goes on in here. You might not see it because my head will be in the way. So it consists of an electron gun. That's this guy over here. It's just a little filament that glows like an incandescent light. And it kicks off electrons. And then there's electrostatic field around there which forces the electrons into what's called a crossover, makes them very small and tight, and then from then on you can deal with that field. You accelerate it and you can get the electrons to go in a nice straight line. Okay, so I can make an electron beam, and I can show you that basically if I simply... can you do me a favour? Can you hit the safety lights? And maybe even this as well. Let's have a look. Yeah. So if I turn this off, I'm not going to see much. I'm increasing my voltage on my electron gun. I'm making the electrons accelerated through a bigger and bigger potential difference. And up to 60 volts and 70 volts and 80 volts and 90 volts and 100 volts and 130. Bear with me. I'm sorry, I'm going to cut you guys off. I might have to do it the other way around. It depends on how the light is. Oh yeah. Can you guys see there's a green beam coming out of that? Can you see it? Going downwards. See it? See it? Nice green beam. Yeah. You see it's going down. What's happening? We've got helium-filled gas. Electrons go through. They hit the outer shell electrons. Boom. They bounce back. Okay. That's what happens now. Bear with me 1 second. Yeah.